We start a new chapter today, and today's lesson, as you can see, is going to be operations with polynomials. And there's two main objectives that I want to accomplish with this lesson, and hopefully after watching this and doing your own practice, you will be very good at multiplication, division, and simplifying monomials and expressions involving powers or exponents. And then we also want you to be really good at addition, subtraction, and multiplication of polynomials. Okay, polynomials really comes from, the word polynomials comes from two words. The poly part of this word comes from a word that means many, and the nomials part comes from a word that means terms. So you put them together, and polynomials really means many terms. And so we're going to be looking at various operations involving polynomials. Okay, but before we can get into our lesson, we're going to be using in this lesson these properties of exponents that you learned in Algebra 1. So we just need a quick review, and hopefully you drilled this a lot. So hopefully after seeing these very quickly, they'll all come back to you, and you will remember how to apply these various properties. The first one that I've given to you here we call the product of powers. And what that means is if you're multiplying two different terms that have the same base, the base means the number below the exponent. As you can see, the bases are the same. They're both x, indicating it's the same number. And when this happens, when you're multiplying and the bases are the same, then you just add the exponents together. You write the base one time, and then you show the two exponents being added together. So here's an example using numbers. 4 to the second times 4 to the third. The bases are the same. They each are 4. So to get your final answer, you write the base, which is 4, and then you add the exponents together. So that's the multiplication of two or more like bases. You add the exponents. Okay, quotient, that's just another word for division. The quotient of powers, well, if it makes sense that if we're going to add exponents whenever we're multiplying like bases, then we're going to subtract. The opposite of addition is subtraction. The opposite of multiplication is division. So in this case, whenever we're dividing and the bases are the same, then once again we're going to subtract exponents. And I've just provided a little blank here. I didn't want you to think that's something that you have to write, but as we go through these notes in class, I'm going to have you guys fill these notes in. So the exponent for the base, the like base, which is x, will be a minus b, the top exponent minus the bottom exponent. And then here's another example, c to the 7 divided by c to the third. The bases are the same, so I just subtract 7 minus 3, and it gives me exponent 4, c to the fourth power. All right, here's this negative exponent rule, and this tends to give people a little bit of trouble. The negative exponent rule or property says that we always have to write the reciprocal of the base. In my example here, the base is x. So whenever I see a negative exponent, I immediately write the reciprocal of the base, and the reciprocal of x is 1 over x. Remember, you can think of x as x over 1. Well, if you flip that over or write the reciprocal, you have 1 over x. So then after changing the base to its reciprocal, then you can write the positive exponent. So x to the negative a is equal to 1 over x to the positive a. And then we'll just do the opposite here. This is showing 1 over x to the negative a. Well, the reciprocal of 1 over x is x over 1. And once we provide the reciprocal of the base, which in this case is 1 over x, then we can write the positive exponent. Now, of course, this assumes that x is not 0, because that would create division by 0, which is mathematically undefined. Okay, so here's another example, a couple examples using regular numbers. 4 to the negative 2 is rewritten as 1 over 4, that's the reciprocal of 4, to the positive 2. And then, of course, that's 1 over 16. Okay, here 1 over x to the negative 7 is rewritten as the reciprocal of 1 over x, which is x over 1, to the positive 7. So again, I'm just providing you a blank there in which to write the exponent answer for your notes. Okay, so that's the negative exponent rule, and it's all about writing the reciprocal of the base and then changing the exponent to a positive. All right, here's another. We call this the power of a power. Here we have a power a inside parentheses being raised to another power b. Whenever this happens, when we have a power being raised to a power, we write that base again. The base is x, and this time we're going to multiply exponents. Okay, here's some examples. 2 to the third, and 2 to the third being raised to the fifth power, that's 2 to the 3 times 5 power, which is 15. Here's another example, the base of e to the fourth, that's being raised to the third, that would be e to the 4 times 3, which is 12, e to the 12th power. So that's an example of a power of a power. We multiply the exponents together. Okay, the power of a product. This implies that two numbers, two or more, could be more than two, numbers are being multiplied together, and the product of those numbers is being raised to a power. Well, this simply says that each of the numbers inside the parentheses that are being multiplied together are being raised separately to that power, whatever it is. So look at my example. I have 3 times x in parentheses, and this product is being raised to the third power. Well, that means that both 3 and x need to be raised to this third power. And then I just took it another step. 3 to the third is 27, x to the third. But the big takeaway here is make sure that you raise everything in the parentheses that's being multiplied to whatever this power is. Okay? And the power of a quotient is similar, except now instead of multiplication, it's division, of course. So we're going to have x to the a divided by y to the a. Okay, those are going to be, it's like this exponent applies to both of these parts of this fraction. Here's an example. X over y to the third means I've got x to the third over y to the third. Okay, with parentheses raised to the third. Here without parentheses, both of these parts of the quotient being raised to the third power. All right, and here's the negative exponent example. Remember, negative exponents force us, they make us write the reciprocal of the base. Well, the base in this case is x over y. That's what's being raised to the negative exponent. So the reciprocal of x over y is y over x. You just flip it over. And then when you change to the reciprocal, notice how the exponent then becomes positive. Okay, you write the reciprocal of the base, then the exponent becomes positive, and now each of these will be raised to the a power. All right, so here's another example. X over y to the negative 4. Well, the negative exponent means you flip it over, you write the reciprocal of the base, which would be y over x, and then you change the exponent to positive, so both y and x will be raised to the fourth power. All right, and let's see, we have one more, and that's the zero power property. And that basically says any number raised to the zero power is equal to 1. Now that's assuming that the base is not 0. Okay? So any number basically besides 0 being raised to the 0 power is 1. And in just a minute we'll maybe help you understand why that can't be 0. So here's an example. I have 8,000 raised to the 0 power. That equals 1. It really doesn't matter what this base number is as long as it's not 0. 2 billion raised to the 0 power is 1. So just a little proof, because I do have, from time to time, I have some people ask me, why is that the case? Why is any number raised to the 0 power equal to 1 as long as that base number is not 0? Let's just take a look at it using one of the rules we've already looked at, this quotient of powers rule. Well, to start with, I just have this simple expression, 49 divided by 49. Of course, that equals 1. We know from our past experience that any number divided by itself is always equal to 1. Well, I just chose another way of writing 49 here in red using an exponent 2. 7 to the second, of course, is 49. So now I'm applying that rule that says if we're dividing and the bases are the same, and they are, the base in each case is 7, then I write that base and then I subtract the exponents. Well, 2 minus 2 is 0. So I have 7 to the 0 power over here, but that's the same thing as equaling to 1. Okay, so hopefully that helps this property, this 0 power property, make a little bit more sense when you apply it with this quotient of powers property. And then this helps us maybe understand why x, or this base, can't be 0, because then we would be dividing by 0. If we used our quotient of powers, 0 to some power divided by 0, well, you can't divide by 0. That's mathematically undefined. So that's hopefully a little explanation as to why this base cannot be 0. Okay, well, that's all of the properties. That's a quick run through, but you'll have these in your notes and you may want to refer back to them if you have questions as you work on the homework. So with that said, let's get into some homework examples. Example number 1, and I've got several that match up with your problems 1 through 4, 16 to 23. The directions from your book say to simplify, and we're going to look at some expressions that we're going to be simplifying, and we can assume that no variable is 0, so we don't have to worry about division by 0. Here's something that I think will be important, because I always have the question, how do I know when I'm fully simplified? How do I know when there's nothing else that can be done? Well, there's basically 4 ways you will know. Okay, and before we get into the actual problems, let's just set them up by making sure you understand when an expression is fully simplified. Well, first of all, there will not be any powers of powers. Okay, so in essence, if you have parentheses, something inside parentheses being raised to something outside, then you should apply that power of power rule, which says in this case x to the a times b. You go ahead and multiply those together with the base being written underneath the product of those two exponents. Okay, so that should be true. No powers of powers. Each base appears only once, so you shouldn't have anything like this, 2 to the third times 2 to the fourth. You should put those together applying your rule of when you're multiplying like bases, you add the exponents. Okay, all fractions are in simplest form. That just means they should be reduced if possible. And then you should never leave an answer with a negative exponent. All right, 2 to the negative 3 is 1 over 2 to the positive 3. And that can be even simplified even further. That would be 1 over 8. So make sure you understand your negative exponent principle. Okay, so with that said, let's look at some examples that hopefully match up pretty closely with your homework. So for letter A, I'm multiplying these 3 expressions together, and to start with, I'm going to multiply the coefficients together. We have 2 coefficients, just mean the numbers that are being multiplied times variables. They're the numbers in front. We have 2 times 3, and then we have this invisible 1. So 2 times 3 times 1, of course, is 6. All right, and now I'm multiplying, so I remember that rule that says if I'm multiplying like bases, which I have here, I have a to the -2 and a to the third, then I'm going to go back to that rule that says multiplication of like bases means I write the base, and then I just add the exponents together. So -2 plus 3 is 1, and we don't typically write exponent 1. It's always understood that if a variable or a number does not have an exponent showing, it's understood to be exponent 1. Okay, there are no other b terms to multiply by, so I'm just going to include b to the second in my answer. And then when I look over here at the c term, I notice that it has a negative exponent. Okay, so all of this is being multiplied together, 6 times a times b squared times c to the -2. Okay, but remember, negative exponents have to be changed, and c to the -2, if I write the reciprocal of c, I'm going to write 1 over c. And then I change the exponent to positive. Okay, well, this would be a terrible way to end this answer because I need to make sure all of this is multiplied together. And it's as though I'm going to say 6 times a times b squared times 1. And all of that will be over 1 times 1 times 1 times c squared. Okay, so that is my final answer. I have no negative exponents. All of my conditions are met from this previous slide. Can't simplify anymore, can't reduce, and so that is a final answer. Okay, let's try letter B. Once again, I'm going to start off by multiplying coefficients. 2 times -7 is -14. All right, now I'm going to multiply like bases, and I'm going to do that by adding their exponents together. So I write the base, and then I'm going to add -3 plus 5, and that's +2. Same thing for the y's. I'm going to write the base, and then I'm going to add 3 plus -6 is -3. All right, well, I can't leave my answer with a negative exponent. And I showed you over here how we just rewrote c to the -2 as 1 over c squared. You can also think of it this way: a negative exponent in the numerator, okay, right now all of this is over 1, becomes a positive exponent in the denominator. Okay, so just giving you two different ways of seeing that. I'm sure you've encountered that in Algebra 1. But I'm double checking, I can't reduce, everything is fully simplified, and so that is my final answer for letter B. Alright, now letter C involves division. So I'm going to begin by dividing the coefficients first. 15 divided by -3 is -5. Okay, my rule of division of like bases is that I write the base and I subtract the exponents. 5 minus 2 is 3. Okay, same thing here. I have like bases. I'm going to write the base. I'm going to subtract the exponents. 3 minus 7. It's the top minus the bottom, and that's -4. Okay, so once again, if you want to, you can think of that as a fraction over 1. And d to the -4 has to be changed to a positive exponent, so it leaves the numerator as a negative and it goes to the denominator as a positive. Alright, so hopefully that makes sense. If it were down in the denominator as a negative, then it would go up to the numerator as a positive. Okay, and that ends up being the final answer for letter C. Okay, letter D. We have this rule of a quotient being raised to a power, And also notice that it's a negative power. So the first thing I'm going to do is apply that negative exponent rule that says I'm going to flip the base, or that's another way of saying write the reciprocal. And then I'm going to change the exponent to positive. Okay? And my next rule is when I have a quotient like this being raised to a power, that means both parts of the fraction have to be raised to that power. And now I don't want to stop here. I know what I can expand 4 to the third power. 4 times 4 times 4 is 64. And I can't simplify, of course, a to the third. And so that is my final simplified answer for letter D. Okay, letter E. This is when we have powers of powers. So powers of powers, or some people call this the power to a power property. Well, everything in the parentheses needs to be raised, in this case, to the 5th power. Okay, so let's just do that first. I'm going to show -2 raised to the 5th. Every one of these terms being multiplied together need to be raised to the 5th power. So what happens when I raise a power to a power? Well, remember that property says you write the base and you multiply these together. 3 times 5 is 15. Okay, when I raise 2 to the 5th power, I write the base and then I say the exponent is 2 times 5, which is 10. All right, and so I want you to always simplify these numbers that are raised to powers. And so remember, this is not a negative exponent, so the only time you write the reciprocal of the base is if the exponent's negative. Well, this is just a negative base. It literally says -2 times itself 5 times, and that should be -32, x to the 15th, y to the 10th. And that's our final answer. Okay, letter F. We do have coefficients here. This would be like -1, and of course this would be +1. And -1 divided by +1 is -1. Okay, and I'll just go ahead and write the -1, and then we'll take a look at whether or not we'll keep it. Now remember our rule, or our property of division of like bases. We have like bases of a's here, and we subtract the exponent. So it's a to the 4 minus 3 power. 4 minus 3 is 1. So once again, I'll go ahead and write the exponent, but we'll probably remove it. We don't typically write exponent 1. Okay, I'll have like bases here as well. And once again, I write the base and I subtract. 6 minus 4 is 2. Okay, and if you left your answer like that, I wouldn't mark it wrong, but I'm hoping that in Algebra 2 we would not do stuff like this, writing an exponent 1, or either even something like this where we show a coefficient of -1. I would rather you just not write the 1 and just show the negative sign. Not that I would mark it wrong, but I think when we get to Algebra 2 we should be a little more advanced. Maybe that's something, a way that you would write an answer in Algebra 1. Okay, so that is your final answer for letter F. Now that was several examples, and I hope that helps you with those problems, and I'll recap the whole assignment at the end. Okay, the next type of problem, my second example, is really an exercise in whether or not you can identify a polynomial. Determine whether each expression is a polynomial, and then if it is, we want to learn, or we want you to understand how to state the degree of that polynomial. Well, let me just run through a quick explanation of how do you know whether or not you're looking at a polynomial. Well, a polynomial should be monomials that are connected with either plus or minus signs. That's kind of a simple way of explaining it. So every one of these separate terms that are connected either with plus or minus should represent monomials. Okay, and monomials, generally speaking, just giving you a quick definition, they have to have exponents that are not negative, not fractions. Okay, they just have to be positive integers. Let me give you some examples and then some non-examples. Okay, here's a good example of a monomial. It could be just a constant, or it could be the combination of constant and several variables. Okay, all being multiplied together. Well, here are some non-examples. Okay, remember I told you that to be a monomial, it can't have a negative exponent. Okay, that is not a monomial because it has a negative exponent. The square root of a variable, that actually is exponent 1/2, and to be a monomial, it's got to be a positive integer as the exponent, and 1/2 is not an integer, it's a rational number. You can't have a variable in the denominator of a fraction. Okay, that's not a monomial. That would be a rational expression, but it would not be a monomial. So with that being said, if you have a polynomial, then all of your separate terms that are added or subtracted will be monomials. Okay, so let me erase this, and then we'll just walk through some examples together. Okay, so letter A, is this a polynomial? And it is, because I have expressions. I don't have any variables in denominators. I have this 1/4, but can't have variables in the denominator. I can't have negative exponents. I can't have fractional exponents like square roots. So the answer to this is yes, it is a polynomial. Okay, and now let's talk about how do we find the degree. Well, the way you find the degree of a monomial is in this case, when there's two variables, you just add those two exponents together. So 4 plus 3 is 7. And then over here we just have one exponent, and it has, or we have one variable, and it has exponent 5. The degree will be the largest number exponent. Okay, so when I add these two together, I get 7 compared to this single variable that has exponent 5. Obviously 7 is bigger, so that becomes the degree. Alright, so that's my final answer for letter A. Letter B, not a polynomial, and we discussed that earlier, because the square root of x, if we looked at that in exponent form, and we will later, that's like saying x to the 1/2 power. 1/2 is not an integer, and to be a monomial, it has to be a positive integer. Since it's not a polynomial, you don't have to worry about the degree. Okay, letter C, also not a polynomial. We have negative exponents, so you don't have to worry about the degree. Letter D, not a polynomial, because we have a variable in the denominator. Okay, what about letter E? Looks like we have a polynomial because each one of these represents monomials. So let's determine the degree. Okay, I'm just going to write it across the top. For this first monomial, we would say 5 plus 1, which is 6. For this second monomial, we would do 4 plus 3, which is 7. And for this third monomial, we would say 1 plus 1, which is 2. And we take the largest as our degree. So this is a polynomial, and it's degree 7. All right, so you're going to do a few of those types of problems where you classify is it polynomial or not, and then hopefully you understand now how to find the degree of a polynomial. All right, finally, my last example is just to simplify polynomials that are being added, subtracted, or multiplied. And this refers to the odd problems, 9 through 13 odd, and then you're going to be doing the 28 to 38 part evens. Okay, so when I'm subtracting one polynomial from another, I'm going to show this one using what we call the horizontal method, and then the next one I'll use the vertical method, and then I'll let you pick which one you like best. When you're subtracting like this, you probably learned this in Algebra 1. I'm going to remove the parentheses before I begin combining like terms, because this really is an exercise in putting like terms together. So remember, when you're subtracting a polynomial, to remove the parentheses, think of the distributive property and think of distributing -1. All right, when I distribute -1 to each of these terms, I get -2x squared minus 3x plus 1. Okay, and now I'm going to put like terms together. So I notice like terms, of course, means they have to have the same variable, and not only that, but the variable has to have the same exponent. So I'm going to put a blue square around a couple of like terms. Okay, those are like terms, and to put like terms together with addition or subtraction, I basically just work with the coefficients. 4 minus 2 is 2, and then I just write the variable and the exponent that is like to both of the terms. All right, that takes care of the x squared terms. Now in green, I'll circle another pair of like terms. -5x, -3x. Those are like terms because they have the same variable, and those variables have the same exponent. They're both exponent 1. So I just operate with the coefficients. -5 minus 3 is -8x. And then finally, let's see, we'll just put a little triangle in black around the other like terms. Those are constants. So we're going to do 6 plus 1, and we get 7. And that's it. That is my final answer. Okay, let's try another example. Okay, this time I'm going to use the vertical method, and maybe you've seen this in the past. The vertical method says that we're going to line our terms up. It's like taking the first polynomial and putting the second polynomial beneath it, but we just got to be careful that we put like terms above each other. Same idea, and I'm going to be adding, of course. So again, if you prefer this method, that's fine. Just make sure that you align your like terms. 6 plus -4 is 2x squared. -7 plus 9 is 2x. And then 8 plus -5 is +3. And that is my final answer for letter B. Okay. Letter C. This time I'm going to simplify by using the distributive property, and I've got an exponent rule that I've got to keep in mind. So let's distribute -2a to each one of these three terms in parentheses. I'm going to multiply coefficients. -2 times -3, that's 6 positive. And now remember, when I multiply like bases, these are like bases, a to the first times a to the second. That's a to the third. Okay, now I'm going to multiply -2a times -11a. That gives me positive 22a squared. And now I'm going to multiply -2a times -20, and that gives me negative 40a. And that is my final answer. All right, now letter D, we have multiplication of these three binomials. And so to start, we just need to pick a pair of binomials. It really doesn't matter which two you choose. I'm just going to put brackets around these two, and I'm going to use FOIL on just these two. Okay, so if I use the FOIL method, I get a times a, which is a squared. I'm going to get minus ab plus ab. It's first, outer, inner, and then I'm going to get minus b squared. Well, obviously inside, these two ab terms are going to cancel each other, so I'm left with a squared minus b squared. Okay, when I put those first two together, that's my result. Now I'm going to take that result and multiply by the other binomial. And once again, I'm going to use FOIL. Anytime you have two binomials multiplied together, you just use the FOIL method. So a squared times 2a. Remember, you multiply coefficients. 2 times 1 is 2. And now for like bases, you add their exponents. So just write the base, and 2 plus 1 is 3. All right, now we're going to multiply a squared times b. Now I'm going to multiply negative b squared times 2a, negative 2ab squared. And now I'm going to multiply these last terms together. Negative b squared times b is negative b to the third, 2 plus 1. And I don't have any other like terms that I can combine. And so that ends up being my final answer. Okay, that is it. Those are all the homework examples I have for you, the notes for this lesson, and that will be the assignment that we check next time. Work hard on it, and we'll see how you did, and if you have any questions, let me know.